Alright guys, here's going to be a quick overview of Station 5, which is dealing with continuity in terms of limits. So I'm not going to spend too much time on these guys right here. 292, it says examine the graphs and determine why each is discontinuous and what is that type of discontinuity. So it is discontinuous at A because there's a hole in the graph, but because we grab this guy up here, this is called a removable discontinuity because that point was actually removed. Same thing here on 294. So again, we have a removable because that value was removed. Down here on 293, the value is not removed, but we jump. So if I were drawing, I'd have to physically lift my pencil up and jump to a new point on the page. So this is called a jump discontinuity. And then our last type is if this guy looks like it's going in different directions. The limit does not exist, but this is an asymptote here. This is called an infinite discontinuity. So remember that these are going to be your three main types of discontinuities: removable, jump. So removable if one point is removed, jump if you're physically jumping to a different location, and infinite if they're heading towards positive and negative infinity. There is a vertical asymptote. Let's look at these next guys right here. Are the following three functions continuous at x equals 1? Justify why or why not using the three criteria of continuity. We'll talk about those three criteria when we get there. The three criteria of continuity are literally like, does f of x exist? Right, so that's one criteria. The other one is the limit of f of x from the right. Whoops. The right-hand limit and the x-hand limit are equivalent. And then the third criteria. So then the third criteria is, does the limit of f of x as x approaches whatever value, does that equal when I plug that value in? So when I actually plug that value in, does the limit equal the same thing as the number? So really we're asking ourselves, like, is there a removable or point discontinuity happening here? Or infinite? If not, then we are good to go. On this very first one right here, we see that if I were to plug in, so this is actually asking continuous at 1. So if I were to plug in a 1, I would get f of 1 equals 0 over 0. So I'm going to say no. And the reason why is because there's going to be some sort of discontinuity here. There's an asymptote at 1. So we're just going to say no and move on. So even if I were able to find a limit, I'm asking about continuity. So I'm going to say f of 1 does not exist. So it is not continuous. I cannot go any further or prove continuity here. This next guy right here, we have a piecewise function. And what's really happening here is this is looking like we have some sort of removable discontinuity. But let's make sure that it is removable and not a continuous line. So first off, let's prove, does f of x or f of 1 exist? If I were to plug this in, this is kind of a funky format. Let's say, does m of 1 exist? So m of 1 equals 3. So that is my first point, my first proof. So it does exist. Now the second thing I need to prove is, does the limit exist? Does it approach the same value? This is not a left or right hand, so I can actually modify this and say not just is the left and right hand, but also does the limit as x approaches said value of f of x, does it exist? Because if it is D and E, that means there's some sort of asymptote. Let's look right here. If I were to factor this function out, I would get z let's see, z plus 2, z minus 1 over z minus 1. So I would write here in my notation, the limit as x approaches 1 of m of 1 is going to equal, if I plug that in here, it does exist, 1 plus 2 equals 3. Now the last thing here is I'm going to say, all right, are both of these things equal? And if both of those things are equal, then it is continuous and it meets the 3 criteria of continuity. We're going to summarize this by saying m of 1 equals the limit as x approaches 1 of m of x. These are both the same thing, and these all equal 3. So therefore, m of z is continuous at z equals 1. And I can go through here, and I might want to modify these to say z if I'm going to use my summarizing statement with that z value. And that is all you have to do here. So you're just proving, does it exist? Does the limit exist? And then do the limit and the actual value of the point or that ordered pair, are they the same? Because what this graph is saying here is that like we're approaching, it looks like we're approaching, we have a hole, we keep on moving, but then this point comes in, this 3, and it fills in that gap, so this graph is actually continuous at that point. Number 309, find the constants a and b such that the function is continuous everywhere. So let's get this done here. Let me get rid of all this work so I can work from a blank slate. So if they are continuous, that means the left and right hand side have to be equivalent. So I'm going to come here and I'm going to say the limit as x approaches 2 from the left of f of x needs to equal the limit as x approaches 2 from the right of f of x. So really what we mean here is that left hand side, that x cubed, needs to equal that ax squared as x approaches 2. So now I'm just going to substitute that 2 in. So I know that 2 cubed needs to equal a times 2 squared, or 8 needs to equal 4a. In this case, I'm just going to simplify and say a equals 2 by dividing by 4. And all we're saying, if that a value is 2, then that function is going to be continuous over said interval and everywhere. Let's get this last one done here. Same thing is going on. We know that the limit as they approach from both the left and right have to equal that value. So the limit of g sub x as x approaches a, we don't have said values here, so I'm going to say as x approaches a, needs to equal the value of g of, if I plug in an a. Now, this looks kind of funky here, but what we're saying here is that it's very similar to that definition of continuity that we did up top. We're saying that the limit of g of x, it has to approach the same number as that plug-in hole. So we're saying that like this function, we don't know what's happening here, but at the value a, something's happening and there's a hole. And we're saying that we want this 8 to be the value that plugs in and fills that hole to make this function continuous. So let's go around here and let's say we know that the limit of x approaches a of x squared minus a squared over x minus a needs to equal 8. If I were to just plug in a right now, this would give me an indeterminate form. So I'm going to factor out. I see difference of squares in the numerator. This is going to be an x plus a and an x minus a. All over x minus a. This needs to equal 8. Let's get this taken care of here. And remember, we're finding the limit as x approaches a. So after I get this simplified, I'm going to substitute in. And I'm going to say a plus a needs to equal 8, or 2a needs to equal 8. At this point, I can go in and solve, and I say, all right, a is going to equal 4. And you are good to go here. 4 is the value that makes that function continuous. Because if I have an x squared minus 4 squared over x minus 4, at that value, it should be equivalent to 8. So we are good to go.